to the lecture for section 12.3. This is MGF 1106, Liberal Arts Math, and my name is Jorge. So in section 12.3, we're going to be talking about permutations and combinations. So the objectives are the following. We're going to calculate the number of permutations of n objects taken r at a time. We're going to use factorial notation to represent the number of permutations of a set of objects. Then we're going to calculate the number of combinations of n objects taken r at a time, and then we're going to apply the theory of permutations and combinations to solve some counting problems. So what's a permutation? Permutation is an order of distinct objects in a straight line. So if we select r different objects from a set of n objects and arrange them in a straight line, this is the permutation of n objects taken r at a time. And the symbol for permutation is denoted by the symbol given here. So the P reminds you of the word permutation. N is the number of objects from which you can select, and then R is the number of objects that you actually select. So here's an example. How many permutations are there of the letters A, B, C, and D? And we're going to go ahead and write this using permutation notation. So now we write the letters A, B, C, and D in a line without repetition. So A, B, C, D and B, C, A, D are two such permutations. So using the slot diagram from the section 12.2, we know that we have 4 choices for the first one, 3 for the second, 2 for the third, and then 1 for the fourth, which gives us 24 possibilities. So writing this using the permutation notation is the number of permutations of 4 objects taken 4 at a time is equal to 24. The next example. So how many permutations are there of the letters A, B, C, D, E, F, and G if we take the letters 3 at a time? So if you notice, we actually have 7 letters. We're going to choose 3. So we're going to go ahead and write this using permutation notation. Now using the slot diagram, we see that we have 7 for the first choice, 6 for the second, and 5 for the third choice, which gives us 210 possibilities. So the number of permutations of 7 objects taken 3 at a time is equal to 210. Now the next thing that we're going to talk about is factorial. And this is going to lead us to the formula for permutations and also the formula for combinations. So if n is a counting number, then the symbol n factorial stands for the product of n times n minus 1 times n minus 2 times n minus 3 all the way down to 1. Now 0 factorial is actually 1. So here's an example. What's 6 factorial? So 6 factorial is equal to 6 times 5 times 4 times 3 times 2 times 1, which is 720. And if you have a calculator, most scientific calculators have both the permutation and then the factorial, and actually they have a third one, which is the combination key in the calculator. So here's another example. Let's go ahead and compute 8 minus 3 factorial. So the first thing we're going to do is we're going to work with it inside the parentheses first. So 8 minus 3 factorial actually ends up being 5 factorial. And 5 factorial is just equal to 5 times 4 times 3 times 2 times 1, which is 120. And then here's another example. So we're going to go ahead and compute 8 factorial divided by 5 factorial times 3 factorial. So now these numbers can get pretty large pretty quickly. So what you want to do is try to cancel out as much as you can before you actually calculate at the end. So here we have 8 factorial. We know that 8 factorial is the same as 8 times 7 times 6 times 5 all the way down to 1. Now 5 factorial, then it's 5 times 4 times 3 times 2 times 1, and 3 factorial is actually equal to 3 times 2 times 1. So if you notice, if we write 8 times 7 times 6, the next thing that we have is actually 5 factorial. So that part and the 5 factorial and the denominator cancel each other out. Now, the 3 factorial is 3 times 2 times 1, which actually equals 6. So therefore that we can cancel out with the 6 in the numerator, and then we end up with 8 times 7, which is 56. So what's the formula for permutations? So the formula for permutations is actually going to be, so the permutations of n objects taken r at a time is equal to n factorial divided by n minus r factorial. So here's an example using this formula. So the 12-person theater group wishes to select one person to direct the play, a second to supervise the music, and a third to handle publicity tickets and other details. So how many ways can the group fill these positions? So there's a permutation of selecting 3 people out of a group of 12. So the permutation of 12 objects taken 3 at a time is then equal to 12 factorial divided by 12 minus 3 factorial. So as you can see, we know that 12 factorial is equal to 12 times 11 times 10 times 9 factorial, 12 minus 3 is actually equal to 9 factorial. So we can actually cancel those out, and we just end up with 12 times 11 times 10, which is 1,320. So the next thing we're going to talk about is combinations. So the formula for computing combinations. Now, if we choose R objects from a set of n objects, then we say that we're forming a combination of n objects taken R at a time. So the notation CNR denotes the number of combinations. Now, also remember that the combinations is equal to actual permutations divided by R factorial, which gives us the formula of n factorial divided by R factorial times n minus R factorial. So a slightly different formula. So here's an example. How many 3-element sets can be chosen from a set of 5 objects? So combinations order is not important. So it's clear that this is the combination problem. So the combination of 5 objects taken 3 at a time is equal to 5 factorial divided by 3 factorial times 5 minus 3 factorial. Again, the 3 factorials cancel out, so we end up with 5 times 4 as our numerator and then 2 times 1 as our denominator, which gives us an answer of 10. Here's another example. How many 4-person committees can be formed from a set of 10 people? So order again is not important, so it's clear that this is the combination problem. So the combination of 10 objects taken 4 at a time is equal to 10 factorial divided by 4 factorial times 10 minus 4 factorial. Here again the 6 factorials can cancel out. And then here we have the 4 times 3 times 2 times 1, and that we're going to go ahead and cancel out the 9 times 8. So we end up with, actually the 9 cancels out. So we have 10 times 3 times 7, which gives us 210. So here we have another example. A syndicate has $15 million to spend on tickets for a lottery. Tickets cost $1 and contain a combination of 6 numbers from 1 to 44. Does the syndicate have enough money to buy enough tickets to be a guaranteed winner? So here's the solution. The combination of 6 numbers from the possible 44 gives us the number of different tickets. So that is the combination of 44 objects taken 6 at a time is equal to 7,059,052. Does the syndicate have enough money to buy enough tickets to guarantee a winner? Now, in a game of poker, 5 cards are drawn from a standard 52 card deck. How many different poker hands are possible? So then here we're choosing 5 cards out of 52. So the combination is 52 objects taken 5 at a time. So then we end up with 52 factorial divided by 5 factorial times 52 minus 5 factorial, which gives us the 47 factorial. And if we do all the canceling out, we end up with 2,598,960 different possible poker hands. Here's another example. In the game of bridge, a hand consists of 13 cards drawn from a standard 52 card deck. So how many different bridge hands are there? So this is a combination problem. So the combination of 52 objects taken 13 at a time is equal to 52 factorial divided by 13 factorial times 39 factorial, which gives us a pretty large number. So another example. 2 men and 2 women from a firm will attend a conference. If the firm has 10 men and 9 women, in how many different ways can the conference attendees be selected? So the answer is not the combination of 19 objects taken 4 at a time, since this includes options like 4 men and no women being sent to the conference. So this is a little bit more involved. The first thing is we're going to select 2 women from the 9, so that's going to be a combination of 9 women selected 2 at a time, and that's 36 different ways. Then we're going to select the 2 men from the 10 available, so that's a combination of 10 men taken 2 at a time, which is 45 ways. So thus, choosing the women and then choosing the men can be done in 1,620 different ways. Here's another one. So a 16-member consortium wishes to choose a committee consisting of a president, a vice president, and a 3-member executive board. So how many ways can this committee be formed? So the first thing is we're going to count it in 2 stages. We're going to choose a president and vice president, and then we're going to choose the executive board from the remaining members. So choose the president and vice president. This can be done in a permutation of 16 chosen 2 at a time ways, and then the executive board is going to be chosen in a combination of 14 taken 3 at a time ways. So that's going to give us 87,360 different ways that we can choose this. And that's the end of section 12.3. Thank you.